Hopefully you have an opportunity to work through this problem, but if not, let's go through and see if we can be able to use the very definition of the limit to be able to find the tangent slope at a specific point, and then define the equation of a tangent line. All right, and then what we'll do is we'll also graph this to make sure it makes sense to us. So we have this function, all right? So we have a little bit more difficult function to deal with. So we have f of x equals x squared plus 3, and we're looking at the point 27, right? So just to kind of get an idea of what we're looking at, we have our quadratic. So we have 1, 2, 3. So we have this point, or we have this function that we're looking at. And so we have the point 27. All right, so let's just assume this is 27, and I know my graph isn't looking all that great, all right, but just as a reasonable approximation, all right. When we're done, what I can do is I can also use a calculator to graph it just to make sure it makes sense to you all. So let's go ahead and be able to use the definition of the limit to be able to find our slope first, all right? And we're going to talk about a very important concept, what this produces. So we're going to start by using this formula. And so our slope is going to be equal to the limit as h approaches 0. Now remember what we're going to do is we're going to plug in a plus h in for x, and then we're also going to plug in a for x. So what this gives us is a plus h squared plus 3. All right, so that's when we plug in a plus h minus quantity a squared plus 3. And we're going to divide all of that by h. Now, clearly, we can't plug in 0 yet for h, so we have to go through our algebra. And what algebra do we have to do? Well, it's pretty obvious. 3's are eventually going to cancel out. We have a positive and a negative 3. But we probably should square out this a plus h. All right, so for those of you that squared it out as a squared plus h squared, all right, don't ever do that again. All right, that is absolutely incorrect. All right, the correct expansion of that binomial is going to be a squared plus 2ah plus h squared. And how do I get that? Well, we turn it into a FOIL problem. All right, so let me do that below. I'm just going to take this animal right here, and we're going to rewrite it as a plus h times a plus h. And we're going to do our first outer inner last. So a times a is a squared. A times h is ah. Inner terms, another ah alphabetically. It's either ha or ah. And then finally, h times h is h squared. And notice that we have two ah's here. All right, so what that turns into is a squared plus 2ah plus h squared. All right, so again, be careful. Do not just make that a squared plus h squared, okay? Unless you want to be wrong, but nobody wants to be wrong. Right, so let's just get rid of all this because we already know what the FOIL is going to work out to be. Right, I'll just keep that up there for a second. Right, so we're going to end up with equals the limit as h approaches 0. And now we're going to have a squared plus 2ah plus h squared plus 3 minus a squared plus 3. And we're going to divide all of that by h. Right, I'm going to get rid of this now because that was the expanded binomial. All right. Now what we can do is just do some algebra. We're going to distribute the negative to these two terms. All right. And it looks like we're going to have some cancellation going on here. All right. So this is now going to be limit as h approaches 0, a squared 2ah h squared plus 3 minus a squared minus 3 divided by h. Now we still can't plug in h, unfortunately, because we'd be dividing by 0. But we can cancel out the a squared terms. We can cancel out the 3's. So what are we left with? We're left with lim as h approaches 0 of 2ah plus h squared divided by h. Notice this can be rewritten as, I'll just rewrite on this line, we can factor an h out from the numerator. And so factoring an h out gives us 2a plus h divided by h. All right. And that's what we're looking for. We're looking for that h in the denominator to go away. All right, once that goes away, then it's free game. All right, so remember, this is our slope, which is the limit as h approaches 0 of 2a plus h. Right? And then finally, we're going to go through, we're going to substitute 0 in for h, and we end up with 2a plus 0. So our slope is equal to 2a. All right, now what is a? Well, a is any x value on the parabola, or we'll just say on the function or on the graph. All right, so if I wanted to find the slope at any point, I could just plug in that x value. Right? And this is a higher level sort of concept that we haven't seen yet. We've been able to find the slope at one particular point throughout the entire semester by finding that secant line and then eventually getting the tangent line. But it was tough because we had to utilize the calculator and we had to just keep zooming in on that point. Well, now we have a function that's able to tell us what the graph, what the slope is at any point on the function, right? And that's called the derivative. The derivative is a function that tells us the slope at any point on the function. Okay, so it is a function that tells us the slope at any point on a graph. Right? We denote the derivative by f prime. All right, so whenever you see this, f prime at a, okay, this is the derivative. Okay, and so in this case, f prime at a is equal to 2a for us, all right, because that was our function that we got. So how does this help us? Okay, well, what we can do now is we can go back and we can substitute the value of x in that we just got at the very beginning. All right, because remember, this is valid for any value of x equals a. So we go all the way back up to the beginning of the problem. And I know we have a mess here, so let's get rid of all this because we don't need it. And remember, we were looking at the point 27. All right, so remember, a is equal to x, which in this case is equal to 2 for this particular problem. So what we're going to do is we're going to substitute 2 back in for a, and that's going to tell us the slope at that point. Okay, so let's go back down here. I'm just going to rewrite what we have. The original function was x squared plus 3, and the point that we were looking at was the point 2, 7. So the slope at a equals x equals 2 is going to be defined as f prime at 2, which is 2 times 2, which by multivariable numerical methods is 4. Right? And that was the answer that we were looking for part A. Okay, so part A basically tells us that if we go all the way back up to the beginning, all right, and I know we did this a while ago, so I just want to make sure that we're okay with what the original problem asked us. The original problem asked us to be able to find the slope by using the definition of this tangent. And this is actually your definition of the derivative as well. So this is the definition of the derivative. All right. I didn't want to introduce that notion in the previous video because the slope was always -6 in the previous video, right? We had a linear function. So it didn't make much sense to have a function that was a constant function that represented the slope, all right? But now it's a variable function. All right, so now what we need to do is we need to find the equation of the tangent line, and then we're going to graph it to make sure it makes sense. So for part B, remember we have the formula y minus y1 is equal to mx minus x1, right? And in this problem, x1 is 2, y1 is 7, okay? So we go back up there, and the slope m is equal to 4, all right? Because remember, the slope is at x equals 2 is 4, all right? So we just found that. So we're just going to substitute. So we're going to get y minus 7 is going to be equal to 4x minus 2. And now we can just solve this right away for y, so that way we can substitute it back into our calculators. Right? So we're going to get y minus 7 equals 4x minus 8, and then we just add 7 to both sides. All right, and clearly that's just going to give us y equals 4x minus 1. So that's a y, sorry, on the left-hand side. So y equals 4x minus 1. All right, so that's our equation of our tangent line. And here's how you can check to make sure that your answer is correct. All right, now the calculator won't give you this, all right, but what you can do is you can get this equation and check it. So I'm going to go into my calculator, and I'm going to graph both of the functions simultaneously. All right, so I'm going to graph the original function, and then I'm going to graph the tangent line. And it should touch at exactly 1 point on that curve. If it doesn't, then we have to do the entire problem again because we messed something up. So I'm going to clear this. I'm going to go to y equals. Now remember our original function. Our original function was x squared plus 3. And then we're going to go down, and we're going to insert the tangent line, which was 4x minus 1. All right. And then I'm going to go ahead and hit graph, and I'm going to nervously hope that it does work. And right now we can't tell if it works because I'm going to have to zoom standard. All right, so this is really cool because now it looks like, it doesn't look like it's really tangent at 1 point. Let me zoom out just a little bit. All right. And what we could also do is we could zoom in, all right, to kind of see like the tangent line or that tangential relationship. So I'm going to zoom in a couple times. And what I'm going to do is I'm also going to zoom in particularly at the point that we're trying to get to. All right, because look, right now, it looks more like a secant line. It looks like it's cutting it, all right? But that's just the limitations of what we have. So I'm going to trace this. And remember, we're looking when x equals 2, all right? So I'm just going to zoom it in right here. That's about as close as we can get. So I'm going to zoom in. And let's see what happens if we zoom in. All right. Now notice that the tangent line, all right, and I'm going to trace this again. I'm going to trace it back to 2. So I'm just kind of zooming in on the point, maybe right about here. So I'm going to zoom in one more time. All right. And it looks like that there's no line. All right. In fact, it looks like that the line kind of just disappeared into the parabola. And that's because it's touching it at exactly 1 point, and that tangent line is so close to the parabola that they actually can represent one another. And you might think to yourself, well, why would I want to use a linear function to represent a quadratic function? Because they're both easy to work with. And the answer to that is you're right. But what happens if you want to use it to represent a trig function or an exponential or a logarithmic function? And for those of you that are computer scientists, you know that runtime is more expensive when you start working with exponential functions or logarithmic functions, especially if you're doing recursion or any sort of iterations going on with that. So I'm going to go back to our graph. And what this does, now what's actually happening with this, I'm going to graph this one on a function. So just to give you an idea of what we're actually looking at here. So that's our original function, and the tangent line is right about here, and it's looking something like this. All right, it should be touching it. It's really tough to draw on my screen, so I'm going to try again. Maybe I should do this. There we go. All right, so that's actually what's happening with this. And notice that it touches at exactly 1 point. Sometimes what you can do is you can use this to approximate the value of the quadratic, all right? And that's something called a local linear approximation because it only really works around 2, all right? So what we say is that this is a local linear approximation of f about a equals 2. And again, for those of you that are computer programmers or computer science majors, this is a really important concept, all right? Now, we don't study it in this class, but maybe in one of your computer science classes, you'll look at it more in depth. But it really does help with runtime, and it helps with the expedience of being able to run and execute programs to where you have a really weird function that takes a lot of memory to be able to compute, because linear is really easy to compute. All right, so just trying to put in context where you might use something like this in real life. All right, now you could find the slope and be able to find the rate of change at any point. And for those of you that are biologists, you might want to try to figure out, what's the reaction time of some sort of medicine over time in the body, or maybe you inject it into an animal, or maybe even population growth and population decay. To really study that, though, you'd have to look at a course called differential equations, where you have to go through and set up the mathematical models to do that. Right? Same thing in chemistry, reaction times of chemical compounds over time, that's a derivative. In physics, rates of change of particles, even spring constants being able to move at a certain rate of change. Obviously in mathematics, derivatives are used all the time because it's in math. So I'm just trying to give everybody an overview as to where they might use a derivative. All right, so that's our definition of derivative. All right, now in the next series of videos, we're going to be taking a look at faster ways to be able to find the derivative. All right, because as you've noticed, to be able to find the derivative is a pretty taxing sort of exercise. And that's only for a quadratic. What if I did something like x to the fifth? All right, so think about that. Well, we would have to have a plus h to the fifth power plus 3. And then to be able to find that, that would be a plus h times a plus h times a plus h times a plus h, etc. And that would be really difficult for us to FOIL out. There are much easier ways to find the derivative, of which we're going to see in the next videos.